Okay, notes 3, margin of error and matched pair procedures. So margin of error for means. Oftentimes in studies, we want to determine what sample size we need in order to ensure a certain margin of error. Remember, we use this formula, statistic plus or minus the margin of error. Our margin of error for a one sample t interval for means is ME is equal to T star times sampling standard deviation divided by the square root of sample size. It says, why can we not solve this for n like we do in confidence interval for proportions? So it says we cannot find T star without knowing the degrees of freedom, which depends on the sample size. We do not know S, since that also relies on the sample data. Our fixes for this problem is to use Z star to estimate T star, and then use a reasonable value for sigma based on past studies. Our margin of error to determine a sample size for a confidence interval for mean is going to look like the equation above, but instead of T star, we're going to use Z star, and instead of sampling standard deviation, we're going to use population standard deviation, or sigma. So looking at the example, it says medical researchers would like to do a large study to determine the mean cholesterol level mu of children aged 5 to 10. They want their estimate to be within 1 milligram per deciliter of the true value at a 95% confidence level. Previous studies have shown that the cholesterol level in children of this age varies with a population standard deviation of 5. What is the minimum number of children the researchers need in their sample to get their estimate they want? So first we're going to write the information that we have. We know our margin of error is going to be 1 based off the information they give us here, that they want their estimate to be within 1 milligram per deciliter. Okay. We know that they're using a 95% confidence interval, which we know we can find the Z star value to be 1.96. And then we're using a standard deviation of 5 because it says from previous studies, the standard deviation was 5 milligrams per deciliter. So plugging in the information that we know, we have using the following equation, ME is equal to Z star times sigma over the square root of n. We have 1 is equal to 1.96 times 5 over the square root of n. On Desmos, we can use our insolve feature, so I would write this as 1 tilde 1.96 times 5 divided by the square root of x sub 1. And it would give me a value of 96.04, which we always round up. And so because of that, we have that they should use 97 children. And again, we always take this number and round up. So next part is talking about matched pair procedures. So it says comparative studies are more convincing than a single sample investigation. For that reason, one sample inference is less common than comparative inference. Study designs that involve making 2 observations on the same individual or 1 observation on each of two similar individuals result in paired data. Recall that a matched pair design is a special case of a randomized block design. Using a blocked variable, subjects are arranged in pairs matched on relevant factors. Matched pairs may be formed naturally or by the experimenter. Every pair receives both treatments. By randomly assigning one treatment to one member of the pair and assigning the remaining treatment to the second member of the pair. Alternately, each subject may get both treatments, and the order that the subject get the treatment is randomly assigned. Paired data comes from measuring the same quantitative variable twice on the same subject. We can find the difference between the two data points for each subject. We can then analyze the differences. We use a one sample T procedure and perform inference on the mean difference, which we define as mu sub D. These methods are called matched pair procedures. The inference steps will look very similar to the one sample T procedures we've done before. So for communication, your null hypothesis is mu D is equal to 0, meaning that there is no difference. And then your alternative would be mu D less than 0, greater than 0, or not equal to 0. Then you would write your alpha, whatever alpha they give you, and then you would check your conditions. The conditions that you would check would be the random condition. You would check for random assignment. Then the normal condition. Remember, for normal condition, we're trying to use the central limit theorem. And if our data is less than 30, we have to graph and check for no outliers or strong skewness. Remember, we're not checking to see that the sample data is normal. We're just trying to see if we can move on and do the inference with the specified population data being approximately normal. Notice that the independent condition is skipped, and that is because this is an experiment. In order to calculate this, we would use a one sample t-test. Here's the formula for t star, or we can find that on Desmos. You would find the p-value on Desmos as well using that t-test once you type in your degrees of freedom, which is n minus 1. And then your conclusion is always going to be within this sentence stem. So now let's look at an example. So in this example, it says that researchers want to determine if a new type of medicine will help lower glucose production in individuals with type 2 diabetes. Because subjects with type 2 diabetes vary in their eating, exercise, and weight loss journey, researchers decided to do a matched pair experiment. For 1 week, individuals will be placed on a new medicine and told to continue with their normal treatment of type 2 diabetes. Their blood sugar will then be recorded as a %. For the next week, individuals will be placed on their current medication for glucose control and told to continue with their normal treatment, and their blood sugar will then be recorded. This experiment will be double-blind, and the order that the subjects receive the medicine will be randomized. The following is the table along with the difference between the current minus the new. So it says, does the data suggest that there is a significant difference between the current medication and the new medication for lowering blood sugar in people with type 2 diabetes? Use a 5% significance level. Okay, so first we're going to need Desmos. So let me open up Desmos. Okay. So on our problem, we had a table, and we are going to, for this table, have to find the x-bar of difference, the standard deviation of the difference, the sample size by counting those boxes, and then, of course, all the other information to solve. Remember, since this is talking about difference, we only really care about that difference data. So I am going to just put in the list for D representing difference. So I have 0.2, 0.1, negative 0.1, 0.2, 0.1, 0.5, 0.3, negative 0.2, negative 0.1, 0.3, and I put an extra comma in there. Okay, negative 0.1, 0.5, 0.7, 0.1, 0.2, and then lastly negative 0.2. So I should have 16 elements because my sample size is n. Well, for my communication part, I'm going to have to find the mean and standard deviation, so I'm going to do that now. I'm going to go to functions, click on mean, and then do the mean for the difference, and I get 0.156. And then I'm going to do the same for standard deviation. Type in my list of D, and I get 0.263. And so I'm going to use this, okay, on my notes, and I'm going to go ahead and put the calculation portion together. Sorry, communication portion. So for communicate, I first have to define mu of D, and mu of D is going to be the mean difference in blood sugar levels between current and new medication. Then I establish my hypotheses, so mu of D is equal to 0. And then if we're trying to find a difference between the current medication and the new medication, they want to see if the, let's see, researchers want to determine if a new type of medication will help lower the glucose production, okay? So that means the alternative means that the mu difference would be positive, because if we are taking the current medication and subtracting the new medication, if the current medication versus the new medication is making any difference, the new medication's numbers should be lower than the current medication, which means when we subtract, we would always have a positive difference. Our sigma value is 0.05, and then on Desmos, we found x bar of D, which is 0.156, S sub D, which is 0.263, sample size is 16, and degrees of freedom is n minus 1, so that is 15. Okay, now we move on to conditions. So remember, this is an experiment, so we're going to skip the independent condition. So for random, we're looking that the treatments were randomly assigned. Okay, and then for the normal condition, our goal is to use the central limit theorem, but if not, then we graph and make sure we don't see any outliers or extreme skewness. So we're going to say since n is less than 30, because our sample size was 16, we graph. Okay, and then remember, we always graph a histogram. Let's see if it will let me bring it up like that. Oh, that's what I was trying to do before. Okay, perfect. So what we're going to do now is we're going to create a histogram for that difference. Okay, give me one moment. Okay, so to graph a histogram, I'm going to go to functions. I'm going to go down to histogram. I'm going to type in difference. Make sure I am left aligned and then recenter it. And notice when I do that, I'm only going to end up with 2 bends. Well, the idea here is I want to have at least 5 or 6 bends, which means I may have to change my bend width. In order to determine what my bend width is, I'm going to take my range of my sample size, so my largest value, which was 0.7, minus my smallest value, which was negative 0.2, I believe. I don't think I had any 0.3s. Yep, so negative 0.2. And then I'm going to divide that by the square root of my sample size, which is 16. And I get 0.225. So I'm going to go ahead and try that out and see if it adjusts my bends. Hello, it's now at that time. I'm recording a video. You can wait in here and I'm almost done. 0.225. So then I'm going to check that for my bend width. We already know 1 doesn't work, so let's see if I plug in that decimal. Yes, so if I plug in the decimal 0.2, I get the following graph. So then I'm just going to graph it off to the side. And then it just needs to be a rough sketch with your labels on both axes. Okay, and then you're going to see if there's any outliers or extreme skewness. So there's no outliers or extreme skewness. So we can move on to the next part of the problem. And now on to calculate. We know that we're going to use a 1 sample t-test for means. So I'm going to go to inference, t-test, type in my difference, create the test. This is a significance test where mu is equal to 0. And then since this is mu is greater than 0, we're going to look at the right side. And this gives me a t-star value of 2.374. And then a p-value of 0.016. So then I'm going to use this to write my conclusion. And so I'm going to say since p-value is 0.01, what did I write? 0.016. Is less than alpha equal to 0.05. We reject the null hypothesis, which means we have convincing evidence that there is a difference in the average blood sugar levels between current and new medicine.